So last time we were discussing linear recurrence relations. And last statement that we proved is that if we have linear recurrence relations of order 2, so if we have sequence an satisfying the identity an is equal to lambda an minus 1 plus mu an minus 2, and if characteristic polynomial x squared minus lambda x minus 2 equals 0 has two different roots named alpha and beta, then n satisfies this identity if and only if there exists some a and b such that an is a times alpha to the nth power plus b times beta to the nth power. And after that, we had a couple of examples, Fibonacci numbers. And there were just a couple of counting exercises. So first of all, what happens if we have one multiple root here? So it means that x squared minus lambda x minus mu is equal to x minus alpha squared. I already mentioned that if we look at all solutions of linear recurrence relations, they formed two-dimensional linear subspace. So if we know a0 and a1, then we can find a2 as lambda a1 plus mu a0, a3 as lambda a2 plus mu a1, and so on. So we have two-dimensional linear space of solutions. So we want to find two linearly independent solutions using this alpha, and then we can prove that all solutions will be linear combination of these two independent solutions. So first of all, of course, if we look at possible solutions, first of all, of course, alpha to the nth power is satisfying this recurrence relation, because if we just use, so if we wrote alpha minus lambda alpha minus alpha minus 1 minus mu alpha to the power n minus 2, then we can rewrite this as alpha to the power n minus 2 times alpha squared minus lambda alpha minus mu. And this is 0 because alpha is the root of this polynomial. So of course, alpha to the nth power will be solution. And another solution, so if you know a little bit about the polynomials with the multiple roots, you know that they can be characterized as polynomials which is have common roots with its partial. So then you can understand. Then also the solutions will have the form n times alpha to the nth power. See, if we differentiate this function by the parameter alpha, then we have something like n times alpha to the nth power. Let's check that this will be also the solution for this linear recurrence relation. So if we take n equal to n times alpha to the nth power, then we have here something like, sorry. So it will be n times alpha to the nth power minus lambda times n minus 1 alpha to the n minus 1 minus mu times n minus 2 times alpha to the n minus 2 power. So again, if we try to find something similar to the previous identity, then we can write something like this. So if we rewrote this as n minus 2 times alpha n minus lambda times n minus 2 times alpha to the n minus 1 minus mu times n minus 2 times alpha minus 2, and so I need to add to this 2 times alpha n minus lambda times alpha to the n minus 1 power. Then we see that this guy is nothing but this times n minus 2. So this will be 0. Already proved it. So all we need to check is that if we so we need to check that this guy is also equal to 0, and we can see that if this is correct, then this is x squared minus 2 alpha x plus alpha squared. So this means that lambda is to alpha, and here we have 2 alpha n minus 2 alpha n, which is 0.
Professor?
So we just checked that we have two these two type of solutions, and they are linearly independent if of course if alpha is not equal to 0. So by this I mean that we cannot multiply alpha n by some constant to get n times alpha to the nth power. Why is alpha is not equal to 0? Because if alpha is equal to 0, then here I should have lambda equal to mu equal to 0, because x squared minus lambda x minus mu is equal to x minus 0 squared. And this means that my recurrence relations was not order 2, but order 0. Because I assumed in this recurrence relations that mu is not equal to 0. So this will be the relations of order 2. So here, in this case, I can resolve just by so if alpha is equal to 0, then m equal to 0, then this is not order 2 recurrence relations. So I have two linearly independent solutions, and so I can state the following theorem. Second theorem about linear recurrence relations of order 2. So if my characteristic polynomial has one root of order 2, then an is the solution of my recurrence relation if and only if an there exists some constants a and b such that an is equal to a times alpha to the nth power plus b times n times alpha to the nth power. And we already, so the proof is similar to the proof of the previous theorem. So I need to check that. So I already checked that all these sequences is the solutions of my recurrence relation. So here I check that alpha to the nth power and n times to the alpha to the nth power are the solutions, and all linear combination of the solutions are also the solutions of this. So I already checked in the previous lecture that if I multiply some sequence by the constant, or just take the sum of the two sequences satisfying this recurrence relation, then we have a new solution of this relation. So all we need to check is that if an is the solution of star, then A can be described in terms of alpha to the nth, a linear combination of alpha to the nth power and n times to the n alpha to the nth power. And so here I can just try to find the coefficients a and b. So I wrote that a0 is equal to a times alpha to the power 0 plus b times 0 times to alpha to power 0, and a1 is equal to so I just want to check that I can find such a and b, that a0 and a1 is satisfying is linear combination of a alpha plus b times n times alpha to the power n. And if this is true, then by recurrence relations I will get that a2 is equal to and so on. So I just want to prove that there exists a and b. If you believe that two guys is linearly independent, and it is true, but I can check it by the calculation. So from this I get that A0 is equal to A, and A1 should be A alpha plus B alpha. So I take B as A1 minus A0 alpha over alpha, or A1 over alpha minus A0. So I can just find the A and B. A is equal to A0 and B is equal to A1 over alpha minus A0. And if I find this relation for the first two elements of my sequence, then for the all others, I talk about the solutions of the recurrence relation. So by solutions, I mean that if I take the sequence Bn is equal to alpha to the nth power, then Bn will be satisfying the recurrence relations that I wrote before. And the same, so is the same hold for the n times alpha to the nth power. I just checked that they are satisfying these recurrence relations. Okay, so for example, so we have an is equal, for example, to an minus 1 minus an minus 2, and here, for example, a1 equal to 1, a0 equal to 1, and a1 equal to 3, and I want to find so I want to find the formula for the an. You can try to solve it, and then we'll discuss, I think, in a couple of minutes. But I need to ask Masoud's question. Oh, here sorry, I need to write this a to the alpha to the power 1. Of course. Yeah, and for a2 we have alpha to the power 2 because so our geometric progressions depends on n. So I just need to take n equal to 2, and then we'll have so if a0 and the 1 satisfies these relations, then we know that an and linear combination of alpha to the nth power plus n times alpha to the nth power satisfies the recurrence relations, and this means that a2 will be equal to this guy, a3 will be equal to the a to the times alpha to the third power, and so on. And for the all others, and the equality also holds. Yes, first of all, you need to find the characteristic polynomial. Then you need to find what is the roots of this polynomial. If we have multiple roots, one multiple root, so you can find the a and b just using this formula. Yeah. So if you write a characteristic polynomial, then you will have like x squared minus 2x plus 1, and yeah, if you find the discriminant, I think you will have 0. Yes. So this means that this polynomial has one multiple root. You can write this as x minus 1 squared. And so we know that the root is equal to 1. Okay, so if you just look at this formula, then you can get that A will be equal to A0 and B is equal to A1 over alpha minus A0. So A0 is 1 and A1 over alpha minus A0 is 2. So n is equal to 1 to the power n, 1 times 1 to the power n plus 2 times n times 1 to the power n, or to n plus 1. And of course it's correct, because if you look at this recurrence relations, then you can see that this means that an minus 1 is the median of an is an minus 2. This means that an is just arithmetic progression, and so if it starts from 1 and 3, then this arithmetic progression is nothing like the odd numbers. So I can rewrite this as an minus 2 is equal to an minus 2 minus an minus 1 minus n minus 2. So this is the difference between the consecutive elements is the same. Okay. Let me give another. Often. So in common situation, you don't have any type of, so you don't have any recurrences, but you in additional you need to find if you have some recurrences in your sequence or not. So another example. So suppose you have let me give two more examples. So first of all, suppose we have a sequences of zeros and ones. Of length n, such that there is no two consecutive ones in this sequence. So an is number of all sequences of zeros and ones in length n, such that there is no consecutive ones in this sequence. So for example, if we have A1, we need to write all the sequences of length 1. If we want to calculate A2, we need to write all sequences of length 2 except for 1, 1. For A3, we have 0, 0, 0, 0, 0, 1, 0, 1, 0, 1, 0, 0, and 1, 0, 1, and so on. So we want to find what is an formula, or maybe so somehow calculate the number of such just sequences of zeros and ones of length n, such that there is no consecutive, there is no two consecutive ones. And maybe I'll give one more example. If someone solve this one. Or maybe I need to write this the same on the same board so you can see it online. Okay, the second task is suppose we have some different types of tiles. So we have I have so suppose I have two different types of 1 times 1 tiles and three different types of 1 times 2 tiles. So I have this type of guys and this type of guys. So how, and the question is, how many different types of type of designs of form 1 times n we can form. So for example, if we have A1, we have only, so A1 is 2, and for A2 we'll have 7 different types of path designs, because I can take, so either I take tiles 1 times 2, or I take green and orange ones and try to put them in different orders. And so again, I want to find what is the formula for the AN.
Can you please explain again what's the rule of doing these tiles?
You have two different types of tiles of length 1 and 3 different types of tiles of length 2. And you want to combine them such we have the path length n. So for example, this, if we want to have a path length 2, then we can just take these guys, one of these guys, or just try to combine these ones. So we can, if I have 1 times n, then I can just try to so firstly I want to have I want to partition this into types of tiles. So this can, for example, will be one type. Length 1, length 2, length 1, length 2, length 2, length 1. And then I just choose the colors here. And I want I want to calculate all different partitions in tiles of length 1 and length 2, and then choose the all different types of colors that I have. So for example, if I want to calculate A3, I need to, so I have these options. I can have all these tiles of length 1. So for here I have 2 options of colors, 2 options of colors, 2 options of colors. Or I have 1 tiles of length 1 and 1 of length 2. Or I have 1 of length 2 and 1 of length 1. So for A3, I suppose that we have here 8 possible variations. This will be 2 and 3, 6 possible variations. And this also will be 6 possible variations. So totally will be 20. I think this is correct, but maybe you need to check it. Okay. So maybe you should first solve first one. It is much more simpler because so we have not so much options for this one. And so the idea for these 2 exercises, first you want to find the recurrence relations. So you want to find how an depends on the previous elements of the sequence. So I want to calculate the number of sequences of length n using the number of sequences of length n minus 1 and minus 2, maybe n minus 3 if I need to. And the same holds for this one, because if I took the all type designs for the length n, I can try to find, so if I know the numbers for the all previous type designs, maybe I can find the type designs for the length n. For example, okay, you have this sequence of length n. Okay, let's look at the last number. So we have 2 different options here. Either the last element of this sequence is 0, or the last element of the sequence is 1. So how many are these types of sequences? How many are there these types of sequences? No, we don't have 2 to the power n because we have restrictions. We cannot have 2 consecutive ones. So do I have, so what's the restrictions for this sequences of zeros and ones? Do you have any restrictions here? Do you have any restrictions here? Okay, so this should be 0, must be 0, yes? But we don't have restrictions here and here, except for this one, yes? Okay, so how many sequences with this form? Which has this form? How many sequences of length n minus 1 satisfying this condition? Each is just an minus 1, yes? Yes? So we have exactly an minus 1 sequences of length n minus 1 satisfying this in this one n minus 2. Okay, so from this we can say that we prove the recurrence relations is just an minus 1 plus an minus 2. We just look at all of the sequences, look at the last element, last number, and so if it's 0, then the previous elements can be any sequences of n minus 1 zeros and ones such that there are no consecutive ones. And if we have 1, then we can have 1 here, so we should have 0 here. And these sequences have length n minus 2. So if you see that example that are right here, so if you look the sequences with the last element 0, we have exactly all the sequences of length 2 here. And if we look at and if the last element is 1, then the previous element is 0, and the first element will be exactly the one element of this. So the sequence is for length 1, and so on. So if I want to look at all possible sequences of length 4, then I can just take all the sequences of length 3 and just add 0 to them, and just take all sequences of length 2 and add 0 and 1 to them. And so I'll have every different possible types of sequences of length n. Okay, so maybe you can find now can I find what is an equal to? So we have here, we have seen this recurrence before, yes? Yes? No?
Yes.
Yeah. And what did you remind us? So what sequences? So what sequence have these recurrence relations? What numbers? Fibonacci. Fibonacci numbers. Okay, is it similar to the Fibonacci numbers? Yes. So how Fibonacci number starts? So we started from 0, 1, 1. So A0 will be, F0 is 0, F1 is 1, and F2 is also 1, and so on. Can we describe AN in terms of Fibonacci numbers? So if I need to write the answer in terms of geometric progressions, then of course I want to write the heuristic polynomial, find the roots of the heuristic polynomial, then find the coefficients so find the linear combination of this progression and try to find formula for the AN. But now I just want to assure that actually AN is similar to the Fn. So we start here from, so we have 2, 3, 5 here. And as the 2, 3, 5 occurs in the Fibonacci numbers, yes, so we can try to describe AN in terms of Fn. Yes? How? Fn. So A1 is equal to F3. So I think we can find that AN is just Fn minus 2 in our definition. So here F3 will be equal to 2, F4 will be equal to 3, and so on. So this sequence is just Fibonacci numbers shifted in the two positions. Now, how do you get this one? Why n is n minus 1 plus 2?
Because if there's minus 1, and only plus 1 more. There's only two choices.
Why do you have plus one plus?
Let me think again.
So you see that a1 is equal to 2 and a2 is equal to 7, so it's not.
Yes.
And if you have something of length n minus 1 and set you have two possible options for this tile, then
No, not only, but the previous also changed.
yeah, so if you have
Yeah, not only two.
yeah, but you don't have to summarize them.
Yes.
Okay, some of you has me showed already the correct recurrence relation. Let's discuss this relation. And the idea is the same as in previous exercise. We want to describe an in terms of previous elements. So again, if we look at this pattern of length n, okay, let's start from the last tile to the right. So which form can be the last tile? We have two options. Either this tile is of length 1, or this tile is of length 2. And so the previous elements form the pattern for n minus 1. So the number of these guys is an minus 1. And the number of these guys is an minus 2. So so we have two possible options for 1 times 1 tiles and three possible options for this type, the type of 1 times 2. And from this we can easily get the recurrence relation for the
union.
Yeah, it's the union of them. So we should we can take the sum of this variations and these variations. But how many possible patterns can we form from n minus 1 patterns of 1 times n minus 1 and two possible tiles of 1 times 1? So if you have two possible options here and n minus 1 options here, then totally we'll have 2 times an minus 1 possible options here. And here we'll have 3 times an minus 2. And so we'll have the following recurrence relation. An is equal to 2 times an minus 1 plus 3 times an minus 2. So from this, you can continue by our algorithm to find the formula for the an. So, for example, this calls for, let's check that. So, for example, 20 should be 2 times 7 plus 3 times 2. Yeah, that's correct. So, it is true for our subsequence here. Did you find the formula? Yes? So you find the roots, but now you need to find the coefficients. So you just take, so the algorithm is straightforward. You just, so you write the characteristic polynomial, find the roots. So that two possible options are they are different, or we have one root of order 2. And so in the first case, you just find, you just need to find A and B such that your sequence is A times alpha to the nth power plus B times beta to the n power. So you just find A0, A1, or A1, A2. You can just, so to simplify this algorithm, you can understand that A0 should be equal to, so if you want this equality holds, then 7 is 2 times 2 plus 3 times 1. Yes, so this will be exactly 1. Tile one pattern of length 0. So you can, so here you have the following system of equations. And if alpha is multiple root, then we already discussed that you need to find some, so you need to find an in terms of linear combination alpha to the nth power and n times alpha to the nth power. So you just can write A0 equal to A and A1 as A plus B times alpha, something like that. Alpha is the root of this characteristic polynomial. Characteristic polynomial can be met by the linear recurrence, just moving them to the one side, and so okay. In this case, characteristic polynomial will be x squared minus 2x minus 3. We just, so if we move this whole equation to the left hand side, we'll have this identity. And from this, we just can write the polynomial of order 2. Polynomial. Yeah. Okay. Now we have two possible choices. Either we have two different roots, or we have one root of multiple root. And in both of these cases, we have, so in this case we have this type of solutions, and in this case we have this type of solutions. Yeah, no, because we always have two different options.
In which case we use
If we have two different roots, then we have just linear combination of these geometric progressions. And if we have one multiple root, so one root of order 2, then we use this formula. So in this case, the roots will be different. So we have -1 and 3. So we can use this formula. Okay, so we can do this calculation. A0 is so the answer will be an is equal to -1 to the n power plus 3 to the n plus 1 over 4. Is this correct? So for example, if n equal to 3, then we'll have 81 minus 1 over 4, which is 20. Yeah, I think this is correct. So the answer is on the board. Okay. So maybe questions, maybe some questions about this exercises or previous. No. So if you want to discuss a little bit more, so how we generalize our result? So we discussed linear reconciliations of order 2, and we have 3 different types of generalization. First of all, what if we have linear reconciliations of order 3, 4, etc.? Can we find the explicit formula for these guys? Second one is, what if we have so-called non-homogeneous linear reconciliations? This means, for example, that we have, Fibonacci relation, but with some constant. For example, we have constant 5 here. So if we know the solutions of the homogeneous linear reconciliations, then we can find the solution for the non-homogeneous, such that if we add there some constants on some linear, so maybe we can find also formula for some linear function of n or something, some function of n, maybe. And of course, maybe we don't have. So what if we don't have linear? So we have relation, but it is not linear reconciliation of some order, but something similar to this. And here we have, I was supposed to, we discussed famous Catalan numbers, which have plenty number of definitions, but with some tricky recurrence relation, which cannot, so it can be, we can achieve formula for the Catalan numbers from these recurrence relations, but it will be not so trivial as we have before. Okay, so let's briefly discuss what happens in the linear constellation of order greater than 2, and we can prove the same theorem, but we need to generalize our 2 different cases here. So we have one case when we have different roots, and the second case when we have multiple roots. And the answer that we can combine them and write some theorem for the arbitrary linear reconciliation of order k. So if we have this recurrence relation, we can find the characteristic polynomial, which is x to the k power minus lambda 1 x to the k minus 1 power minus lambda 2 x to the k minus 2 power, and so on. And we find all the roots of these polynomials. And if we have multiple roots, then we can find their degrees or orders. So suppose we have alpha 1 root of multiplicity g1, alpha 2 multiplicity g2, and so on, alpha s with. So what term do you use to describe the number of alpha occurs in the polynomial? Degree, multiplicity? Multiplicity? Yeah? So I just want to say that this polynomial is equal to x minus alpha 1 to the power j1, x minus alpha 2 to the power j2, and x minus alpha s to the power js. So this, I know in some books they call it degree or multiplicity. Yes. So how do we call it? Multiplicity. Okay. Yeah. Okay. So if you have alpha 1, so the multiplicity of alpha 1 is j1, the multiplicity of alpha 2 is j2, and so on. Then an satisfies linear reconciliation of order k if and only if an can be defined as alpha 1 to the power n plus some bracket times alpha 2 to the power n, and so on. And in brackets, we need to write the polynomial of n of degree j multiplicity minus 1. So for example, here I should write something like a10 plus n times ay1 plus etc. plus n to the power j1 minus 1. Okay, maybe I should write this on the next board so we can see the whole formula. N is equal to a10 plus a11 times n plus n times 2 times n squared plus etc. plus a1 g1 minus 1 times n in the power g1 minus 1 times alpha 1 to the nth power. And the same holds for the all other roots. 2, 0, 2, 1, n, 2, j2 minus 1, and g2 minus 1, alpha 2 to the nth power, and so on. So we see that in case of So if n equals 2 and alpha 1 have multiplicity 1 and alpha 2 is have multiplicity 1, then we have that an is, so j1 minus 1 is 0, so we have exactly one coefficient, and we have the formula that we already knew. So we have just linear combination of geometric progression. And if we have one root of multiplicity 2, then an is equal to a10 plus a11n times alpha n. So we have, so we already also have some of geometric progressions, but multiplied by some polynomials of n. And the idea of proof of the theorem is the same as two theorems that we already proved. So we need just, so first we need to check that all possible solutions form the k-linear subspace in spaces of all sequences, because all sequences depend on the only on the first k coefficients. And then we need to check that we find k linearly independent solutions. And so we need to check that these solutions are all, so all these sequences is linear in solutions, and they're linearly independent. And from it we can prove the theorem. Okay, so you now know what happens if we, for example, have linear reconciliation for the 3. But of course, if you have linear reconciliations for the 3 and greater than 3, then we have a problem of finding the roots. So as you know, not every polynomial of degree 5 or and greater can be solved by formulas. And if you need to solve a polynomial of degree 3, then we have some, we need some use of complex numbers, and there are no trivial formulas. So maybe you cannot find the, using computers you can find the just approximation of solutions, but it will be helpful to find the formula for the an. Okay, so what about, so this is about the first question. What if we have non-homogeneous linear reconciliation for the 2? So suppose we have some shifts. So for example, we have recurrence relations of form, so we have recurrence relations plus, for example, some constant. Can you solve this one, for example? Do you have idea how to find the formula for the Fibonacci numbers, but with shifting? So for example, we start from the same number, so a0 is 0 and a1 is 1, but now we use this, so we have plus 5 here. So do you have any ideas of how can we find the solution? So if you I can be sure that if I knew how to solve linear constellations, then it will help me to find the solution of the shifted. If you want to find the solution of some non-homogeneous equation, then so if you want to find all the solutions, you can try to find some partial solution. So for example, suppose we have two different sequences satisfying this equation. Then if you take, if you subtract one from the other, then we will have then we can see that the difference between two solutions of this equation is just the solution of the homogeneous linear reconciliations, and this we can find. So if we know the partial solution, so if I know the partial solution, then I can just write the formula. Then I can write that, okay, for example, Bn. Then A is equal to Bn plus the solution of the homogeneous linear reconciliation. So in this case it will be A times 1 minus square root 5 over 2 times in the nth power plus B times 1 plus square root of 5 to the power n. So all we need to find, if we can do this, is find some partial solution of this linear reconciliation. And then we can find, so if we want to find exactly this type of solution, we just use this formula and find A and B such that this holds. So if we want to find partial solution, we can just use the some easy type of the sequence satisfying this reconciliation. So for example, I don't know, can we find some simply type of solution here? For example, I don't know, take A0 0 and A1 also 0. Then what should be this sequence? Can we find the formula for the sequence if A0 and A1 is equal to 0? 20, 35. So I just 60, 100, yes. If you divide it by 5, it will be 0, 0, 1, 2, 4. Maybe you can find some.
So we'll meet those sequences and get the partial solution.
Do you find some similarity to the other sequence? Yes? No? No?
Is an equals to a minus 1 plus a minus 2 plus 1.
Yeah, of course. I just divided this all by 5 because if we can find this sequence, then we can find this sequence by multiplied by 5. But I think that this sequence you can remind of something similar to the sequence that we discussed before. No?
We're gonna have like Fibonacci.
Yeah, it's similar to Fibonacci, but Fibonacci. So if I wrote the Fibonacci sequence, then you can find the similarity between these two sequences. Yes, because this is nothing but Fibonacci numbers minus 1.
Yeah, shifted by 1.
Yeah, shifted by 1. Yeah.
Doesn't matter.
Okay, so here the partial solution Bn will be equal to something like 5 times Fn shifted plus sorry. So this sequence is Fn plus 1 minus 1, and Bn is 5 times here n plus 1 minus 1. But actually we can just so the idea is that if we so the answer is the following. So if you want to find the partial solution of this guy, you take just if you take Fibonacci numbers 1 to 5, then we can check that the equality will be true because Fn is equal to Fn minus 1 plus Fn minus 2, and so this minus 5 plus 5 will be cancelled, and this minus 5 with this minus 5 will be cancelled. So if we so if we have just constant here, then we can find partial solution in terms of partial solution of the homogeneous linear equation, and then add it to the and we can describe any solution in terms of this one. And of course, I can just say that we can take Bn is equal to minus 5, simply because minus 5 is minus 5 plus minus 5 plus 5. So we can find just the constant solution of this equation. So if we have non-homogeneous equation, then we can, if we can find the partial solution, we can find the solution to the this also for this equation. So we just need to just take n as 0 and as 1, and find the coefficients a and b such that s0 is 0 and the 1 is 1. And so this will be the answer. You can just do it by yourself, I suppose.